Hi, I'm Doehyun Baek from KAIST. Today, I'm going to present Wasm R3, a record, reduce, replay framework for realistic and standalone WebAssembly benchmarks. This work was a collaboration with researchers from the University of Stuttgart, Google, and Carnegie Mellon University. One of the explicit goals of Wasm from the beginning was to achieve consistent near-native performance. This was pursued to meet the requirements of many complex and demanding web applications, such as 3D visualization, audio software, and video games. So, how do we determine if the Wasm code rewrite is fast? This is usually done by using some benchmarks to measure the performance of the Wasm application under various workloads. On the left is a figure from a PLDI 2017 paper that first introduced Wasm to the academic community. It states, quote, "The results show that WebAssembly is very competitive with native code, with 7 benchmarks within 10% of native and nearly all of them within 2x of native," end quote. In summary, they claim that Wasm is fast. But there was an interesting paper that was presented in ATC 2019, which was titled Not So Fast. They showed that if you only see the results from Polybench C benchmarks on the left, which PLDI paper used for its performance evaluation, it seems that Wasm is competitive with native performance. But if you run these Wasm engines on spec CPU benchmarks on the right, you can see that Wasm is considerably slower than native execution, which is contrary to the results shown by Polybench C. So we can conclude that good benchmarks are important to accurately represent the performance of Wasm. Do we have them? Unfortunately, that has not been the case until now. On the left is a meeting note of the WebAssembly CG meeting held in December 19th of 2023. There was an agenda about creating a new benchmarking subgroup. It was said in the meeting that although people have been reluctant to create an official benchmark suite, it's now the time to collaborate people's efforts to create good, representative benchmarks in the Wasm space. Benchmarking subgroup is created as of January 13th, 2024, confirming the demand for a good benchmark across industry and academia. Despite the demand, why hasn't there been good Wasm benchmarks? We think it is due to a few challenges we have identified in creating Wasm benchmarks while doing this work. Manually creating and maintaining benchmarks, though effective, requires serious engineering efforts. Porting existing native applications into Wasm require good support from efforts like WASI, but it is still lacking in maturity. Extracting benchmarks from real-world web applications require emulation of the web host environment, as they are dependencies of the Wasm applications on the web. We found one technique in the literature that automatically deals with any host interactions that an application has, which is a record and replay. However, previous record and replay approaches had limitations that made them inappropriate to apply in our context. Pinplay, although it supports recording of execution across architectures, it does not support replay across different architectures. JSBench does not record all memory loads, which mean that the replay execution might diverge from the original execution. Jalangi only supports record and replay of JavaScript applications. To solve this problem, we have designed and implemented Wasm R3. Wasm R3 is the first record and replay framework for Wasm. Wasm R3 supports recording at any major web browsers and then produces replay benchmarks executable on any Wasm engines, web or non-web. How does Wasm R3 achieve this goal? I first give a brief overview now and explain the 3 phases of record, reduce, and replay in detail later. The record phase can be considered a front end of Wasm R3. It takes a Wasm web application consisting of a Wasm module and a host code as an input and produces a trace as a result. Wasm R3 intercepts the instantiations of the Wasm modules, instrument the Wasm modules, and then run this instrumented module in the record runtime. Record runtime tracks all function calls and returns, and all loads and stores the mutable states, then serializes these events into a trace. For complex applications, the trace can grow prohibitively large. Thus, to reduce the size of the trace, we apply the shadow memory optimization and call stack optimization on the trace to reduce the size. By these optimizations, we can only keep parts of the trace that are strictly necessary to replay non-determinism that occurred during the execution. Lastly, the replay phase generates a standalone executable replay benchmark by combining the original Wasm module and the replay functions generated from the trace. This is done by first translating the trace into a replay IR, applying several optimizations on top of this replay IR, and then generating replay functions at last. Wasm R3 is able to generate 3 different formats, making replay benchmarks runnable in diverse environments, both web and non-web. We capture all sources of non-determinism introduced by the host functions with a data structure called trace. Trace is just a sequence of events, and in this figure, 6 kinds of events are presented. Func entry and func return events represent the entry and exit of a Wasm function, respectively. Call and call return events represent the point of the program just before and after the call to the other functions. This other function can either be other Wasm functions internal to the module or the host functions that are important. Load and store events represent the various load and store instructions in the Wasm modules, and their respective input and output values are recorded. This is a simplified presentation for brevity, and in the real implementation, we also track mutation to globals, tables, and growth of memory and table. Wasm R3 uses bytecode rewriting of Wasm module to record interactions with the host environment into the trace, and this has the advantage that Wasm R3 runs without any modification to the language runtime, web browser, or OS. We employ 2 kinds of trace reduction in the implementation, but for now, I will only present call stack optimization for the sake of brevity. Call stack optimization's purpose is to only keep events that are related to control flow transfer between the Wasm module and the host, filtering out the events related to control flow transfer between functions inside the module. This is because control flow transfer between the functions in the module is not required for replaying the non-determinism caused by the host functions. On call event, by checking the index of the function called, we determine whether the call is to the internal function or to the imported function. At the first call event, this is a call to the imported function, so this event is kept. At the second call event, this is a call to the internal function, so this event and the following 3 events are discarded because they are not needed. This way, we're able to filter out 6 out of the 10 events, making our approach scale to big Wasm applications. Lastly, after the trace is generated in the record phase and optimized in the reduce phase, we finally turn them into an executable replay benchmark in the replay phase. Optimized trace get first converted to a replay IR with an algorithm presented in the right figure. Let's first look into the type definitions of the replay IR. A replay is just a mapping of a function index to a function. Then, a function is a sequence of context, and a context is a sequence of actions. We divide actions into these 2 tiers to differentiate effects performed by same host function in different invocations. An action corresponds to a single instruction in the host. In the case of export call, this would be calling into a function exported by the Wasm module, and in the case of mutate mem, this would be memory mutation performed on a memory exported. Converting optimized trace into replay IR proceeds in a single pass manner, iterating over trace and doing a case analysis on the type of an event. We carefully implemented this part to reason at what exact point the action should be placed to mimic the original execution in the replay benchmark. On top of this replay IR, we apply several replay optimizations and then turn the optimized replay IR into an actual replay benchmark, which is a straightforward mapping of a replay IR to the corresponding language definitions. To evaluate Wasm R3, we have addressed 4 research questions. For the sake of brevity, we omit the presentation of RQ4 in this talk. For RQ1, we have collected URLs of real-world Wasm web applications and filtered them down to 43 to serve as our evaluation targets. If you read along the third column of the table, you can see the web applications under our targets are composed of applications from various domains. First is programming language implementation, and second is a physics emulator, and third is a video game. From these various real-world web applications, Wasm R3 successfully produced accurate replay benchmarks for 27 out of 43 applications. Replay benchmarks we produce are executable on all 3 web engines and all 3 non-web engines that we used for our evaluation. For RQ2-1, we evaluate the record overhead of Wasm R3. We measured the total CPU cycles spent by the Chromium render process of the target application, once with the uninstrumented application and the other with the instrumented application. You can see that the slowdown is generally modest, with a geometric mean of 3.4x and all but one application exhibiting less than 8.2x overhead. For RQ2-2, we evaluate the performance characteristics of the replay benchmarks generated. We measured the proportion of CPU cycles spent in the replay function out of total CPU cycles spent in the replay benchmarks. You can see that the proportion of replay function is generally low, with the geometric mean of 0.2% and the maximum being 39%. Although this varies with the application's nature, it assures us that most of the time is spent exercising the logic of the original application. This makes replay benchmarks generated by Wasm R3 suitable for the purpose of evaluating the Wasm engines, as we want our benchmark to match our original application behavior as close as possible. For RQ3, we evaluate the effectiveness of trace reduction. We record traces with and without the trace reduction and compare the number of trace events recorded by Wasm R3. You can see that the trace reduction reduced the number of traces to only 0.47% of the original size, which is more than a 200x reduction. During the development process, Wasm R3 failed to produce replay benchmarks without these optimizations, so we believe the trace reductions are essential to the applicability of Wasm R3. To conclude, we present Wasm R3, the first record and replay framework for Wasm. From the real-world applications, it generates a standalone replay benchmark executable on any Wasm engines, web or non-web. It is available as open source, and we hope this contributes to a new era of Wasm benchmarking by enabling generation of benchmarks on demand when the need arises. Thank you. I actually have prepared a 10-minute live code demo session. Should I do this now and then get the questions later?
Yeah, definitely. Demo.
Yeah, I think, yeah. Let's proceed with the demo then. Can everybody still see the screen now? Thanks. So this is a demo showcasing Wasm R3's capability. So let's first look into this app that we're going to run today. This is an app called Funky Card. This is a video game that has a Wasm module as one of its components. Be aware that we're running this application in the original uninstrumented version. And if you open the developer console, it consists of this HTML file, JS file, and this Wasm file. Let's download this for future use. So how do we actually use Wasm R3 on this web app? To run Wasm R3, you just type npm start and then the URL of the web app. It takes some time to load. And then you can just play it as you did previously. Now, be aware that we are running the application in the instrumented state with the Wasm R3, so you can observe some noticeable slowdown here. But I think it's still the stage that is playable in my opinion. I'm now going to stop the recording. This will first download the WebAssembly module, and then this is going to generate a benchmark. This is going to take around like 20 seconds last time I did this. So we should patiently wait. So at last, the benchmark is generated. And if you do not pass it, additional command line arguments, outputs will be saved into a directory starting with benchmark as a default. And as we are generating a benchmark per Wasm module, we should look into this bin0 subdirectory. And here you can see all the files that Wasm R3 have downloaded and generated. And the two important things that you should keep in mind is this index.wasm file and this trace.r3 file. The index.wasm file is just a download of the original Wasm module. And as you can see, the size of this index.wasm and this demo.wasm we just downloaded is exactly the same. You can see that they are actually the same file. This trace.r3 is actually a textual representation of the interactions between the Wasm module and the host environment. There are almost 2 million events in this trace file, so it's quite big. One cool thing about Wasm R3 is as we are using bytecode rewriting, we can actually record on all the major web browsers. So if you pass --webkit to the command line, the Wasm R3 attached to WebKit is going to open up. And this works exactly the same way as it did with Chromium. And if you pass --Firefox in this case, this is going to open up Wasm R3 attached to Firefox. And this is also going to work exactly the same way as it did with Chromium and WebKit. So now we have actually covered a record phase and how it does its serialization into a trace in all the web browsers. So now let's take a sneak peek into our second phase, which is a reduce phase. One problem we have is the trace you have seen is actually already reduced. So we have to add some more logging to see the effects of this trace reduction. I've prepared a simple patch that tracks a total number of function entry events before and after the reduction and logs the ratio of the two. You can see the contents of the patch here, and this is just very simply calculating the ratio and logging the value into a JavaScript console. And if you apply this patch and then run Wasm R3, As you can see from the console, the proportion of the amount of trace left after reduction is almost 0.01%. This is expected, as I said, as most of the function entry events happening is intra-WASM calls, and they get all filtered out because they are not needed for the replay. This helps immensely and make Wasm 3 scale to interactive apps like Funky Card. So we've now seen first the record phase, and secondly, the reduce phase. So let's take a brief look at the replay phase, which is our final phase. Let's go into the benchmark that we created. And we can first try running the original Wasm application in Wasm time, a non-web WebAssembly engine. So if you type time wasm time index.wasm, this of course is not going to run because, as you can see, it is missing this import from the host environments, and also Wasm time doesn't even support all the web APIs that are needed to make applications like this to run. And instead, if you run Wasm time on our replay benchmark, it is going to complete normally. This is because we have all the missing imports filled out with our replay generation technique. And this is, I think, quite amazing. So how does Wasm 3 actually achieve this goal? And to actually find out how, I think it's instructive to compare the original Wasm module with the replay Wasm module side by side. On the left is the original Wasm module from the web application, and on the right is the replay Wasm module that Wasm 3 has generated. They all seem very similar, but one thing, if you scroll down, is that the replay module that we've generated is missing all the imports. And to actually see what happened, we have to see what happened to the call sites of this end-a function, which is a zeroth function in this case. So there are actually 12 call sites of this function. And if we search in this case, so you can see that they are exactly the same code, with the exception that these calls to zeros and third function are replaced with calls to these magic replay functions. And to see how actually these functions look, we can search to their definition. And you can see that instead of being an imported function, this now is a function that is bundled together into this replay Wasm module. This function has the same effect as what imported function did in the original execution, but this is now self-contained in the replay Wasm module. So this was a brief walkthrough of how you use Wasm R3, a sneak peek of how it works. And I hope you enjoyed it and have a good time today. Thank you.
We have time for a couple questions.
Very cool project, very cool demo. Thank you. Does it support Wasm GC at all? And if not, do you think it would be difficult to add support?
Currently, we support up to Wasm 2.0, except SIMD, which we plan for future support. And for the upcoming proposals, especially those in phase 4, we believe there are some proposals that we already support, like multiple memory, because they are not that technically hard. And about the GC, we believe our approach is applicable to Wasm GC also, but we don't have implemented yet. And this is our future work for sure.
I'll expand on that a little bit. So Wasm GC, so he didn't talk about how the shadow memory optimization works, but it basically makes a duplicate of all mutable state So you need to keep a shadow copy of GC state. And in order to compare the shadow copy with the original copy, you need to be able to compare values. So you can do that in the host. You can do that in JS, but you can't do that in pure WASM. So it would require the instrumentation to be dependent on JS. So the technique you talked about here actually works in any host environment as well, not just the web. But WASM GC, there aren't operators in WASM GC yet that will allow you to do it.
Any host environment? Well,
Theoretically, I mean, this demo, we did it in the web, but like the technique should apply to any host environment.
would you need like Aussie or something to record the trace, I guess? Or-
You just need something to get the data out of the market. It puts it internally.
It's a fantastic presentation. I was wondering if like looked into using this record and replay technique in order to enable removable debugging, maybe like time travel debugging, like
Haven't actually used this tool debugging yet, but like during the development of the replay benchmarks we have created led to some, as I know, like crashes in Wizard. So I think it helped implementation debugging of Wizard in some cases. And also, one of the future works we are planning is to actually use this technique to debug the performance difference of WASM engines. So we're definitely planning to utilize this technology to have some crisp, self-contained executable format of WASM application.
Are you observing what NAND bit patterns that you're getting and using that, putting that into the trace?
I think I didn't understand the question. Like what I lost.
So the exact bit pattern of NANDs is and I'm wondering if that ends up in your trace or if you kind of capture that non-determinism in some other way or not.
I think pattern of like what? I think I didn't get the word.
IEEE 754, not a number.
NAND. Personally, I haven't really looked into like if there's any pattern of NAND. So I think I can.
Short answer is no. You'd have to instrument things that could produce non-canonical NANDs.
So really cool work. Thanks. So especially for the debugging thing, it's nice to think about having a low overhead way of running this in production, right? So I'm wondering if you've thought about optimization techniques that you could do to have a lower overhead record. I saw you have like a up to 4x overhead or something like that. Like you could use virtual memory tricks for memory. You could use hardware features for like LBRs on developer branches. Like, have you thought about that at all?
Actually, we are aware of some like hardware record and replay techniques. During the during we did our record and replay, but for this work we didn't have that amount of like always on like very low overhead record as our target because there were some like our requirements was that we don't do any like library OS like browser support, and we just purely rely on bytecode instrumentation. So for this work, that was not like a scope of our project.
I think there might be a little bit that we can gain if we do this directly in the engine. You can emit a little bit more efficient sequences. I think all the loads actually end up being a call that has a couple of compares in there. So we could probably get it down a little bit. We talked a little bit also about doing static analysis because you don't have to instrument every load in store. It's only the ones that could load for mutable shared state. So if you have like a trace and you see that 80% of your program actually doesn't deal with mutable state, you don't have to instrument those. So I think there's some work to be done to bring that down.
You showed a table where not all of your test cases were able to pass. What were some of the reasons for why it doesn't work today?
I'm sorry, I think I didn't get the question.
Maybe our mic isn't working super well.
Turned off.
Oh, turned off? Yeah, okay.
Look back on the left side.
That's not
Yeah.
How about now? Better?
I think it's way clearer. Thanks.
Okay, that's it. Okay, great. So early on in your presentation, actually slide 28, I think it
Yes.
was maybe.
Slide
You showed a table of a lot of different test cases, and a significant number succeeded. It sounds like without any changes. That's amazing. I'm curious, what were some of the reasons why some of the other ones failed? Do you know why?
During the process of this research, we've actually classified them into some known like issues and some like unknown issues, and among the known issues, like half of it is our implementation issue, because this is pretty much a very much like research prototype, so we need to make this better to support these, and half of them were like library dependencies. So the binary, I mean, like bytecode rewriting library we use is Wasabi, but it doesn't support up to certain proposal, so it just cannot instrument it or something like that. And rest, we are like trying to investigate everything, but yeah, we couldn't.
Got it. Thank you.
There's also a question on the Zoom. I'll read it. How do you envision to generalize the approach to also measure interoperability scenarios where we want to also measure calls to the external world?
I don't think I get the like external world, what it precisely means. So measure calls to the, I think in the context of WASM, all the interaction between the WASM module and the outside is this clean import function boundary. So I think like, I'm not exactly sure what the external world means in this context, but yeah, I think that import of like function from module to like host is a clean boundary, so that can generalize to other scenarios.